Aerological diagrams. An aerological diagram is a diagram on which we can display, calculate, perform various processes that happen in the real atmosphere. It's where we can graphically represent temperature and moisture profiles above a station with decreasing pressure. These parameters are measured by balloon launches, shown in the photograph in the top left. We want to be able to display conserved quantities, because these are the sorts of important quantities we assume are going to occur in the real atmosphere. We need to be able to account for phases of water, not just vapour, but also liquid and solid forms. And we want to, as I said before, represent processes that occur in the real atmosphere, like cloud formation, the occurrence of precipitation, fog formation, icing, and indeed turbulence. You can see on the right hand side that we have an aerological diagram. That's the one that's used in the Bureau. On the right hand side are wind barbs, representing how the wind changes with height, and then there's two sets of lines. On the right hand side is the temperature in red, in blue is the temperature profile from 12 hours ago, and on the left hand side of the figure is a measure of the moisture, which we'll define much later. There are some desired properties of an aerological diagram. Firstly, we want an enclosed area to represent energy of some process that occurs. And that will become useful, for example, when we're looking at the energy or the energetics of deep convection. So when we're considering things like thunderstorms. We want as many straightish lines as possible for the main variables that we're interested in, and that's a function of usability. It needs to be legible. We want a large angle between the isotherms, that is the lines of constant temperature, and the dry adiabats, the lines that represent the conserved process of parcels of air ascending and descending without exchanging heat with the environment. And that large angle means that we can distinguish between a process that conserves temperature and a process that conserves heat. We also want a large angle between dry and saturated adiabats in the lower troposphere. We'll define what a saturated adiabat is in a later lecture. So we need to be able to see very clearly the difference between wet and dry air. And we want pressure to decrease upwards because that's common sense. That's exactly what it does. The aerological diagram that we use mostly in the Bureau is the skew T log P diagram, otherwise known in the Bureau as the F160. It's simply the number of the form. So we have the vertical axis as minus logarithm of pressure. So pressure is displayed as a logarithm decreasing upwards, and the temperature lines, the isotherms, are skewed at 45 degrees so that we can distinguish those from the dry adiabats and the saturated adiabats. Remember that the process where temperature is constant is isothermal, a process where the pressure is constant is isobaric, remembering that bar is a unit of pressure, and for usability, the isobars and the isotherms on this diagram are straight lines, as shown.